C++20 standards introduce 5 comparison categories. The first is weak equality. Then follows partial ordering. Partial ordering inherits from weak equality. Then weak ordering. Weak ordering inherits from partial ordering. Then comes strong ordering. Strong ordering inherits from weak ordering. There is also strong equality. Strong equality inherits from weak equality. Also, strong ordering inherits from strong equality. So, 1, 2, 3, 4, 5 comparison categories are introduced in C++20 standard. Weak equality models equivalence relation, and partial ordering models partial order, and strong ordering models total order in mathematics. Of course, total order is most frequently used in common mathematics, but partial ordering is used quite a lot in C++ language. Partial ordering plays very important role in C++ language itself. In this episode, I will talk about partial order or partial ordering. I will briefly explain what is equivalence relation, what is partial order, what is total order, the difference between partial order and the total order in this episode. The best material for learning these things is this book, Schaum's Outline of Set Theory and Related Topics. This book is pretty short, and this book explains very well about relations and set theories. STD weak equality models equivalence relation. Don't confuse weak equality with weak ordering. A relation R in a set A is an equivalence relation if R is reflexive and R is symmetric and R is transitive. Reflexive means for every A in A is related to A. Symmetric means if A is related to B, implies B is related to A. Transitive means if A is related to B and B is related to C, implies A is related to C. A relation R in a set A is an equivalence relation if R is reflexive, that is, for every A in A is related to A, and R is symmetric, that is, A is related to B in R, means B is related to A. Transitive means if A is related to B and B is related to C, implies A is related to C. The most important example of an equivalence relation is that of equality. For any elements in any set, A is equal to A. If A is equal to B, implies B is equal to A. If A is equal to B and B is equal to C, implies A is equal to C. This part is reflexive. This part is symmetry. This part is transitive. So STD weak equality models equivalence relation in mathematics. Again, weak equality defines equality. STD partial ordering models partial order. STD strong ordering models total order. The difference between partial order and total order is that in case of partial order allows incomparable elements. In case of total order does not allow incomparable elements. A relation R in a set A is a partial order if R is reflexive and R is anti-symmetric and R is transitive. Reflexive means for every A in A is related to A. Anti-symmetric means A is related to B and B is related to A implies A is equal to B. Transitive means A is related to B and B is related to C implies A is related to C. If a relation R in a set A satisfies three properties, reflexive, anti-symmetric, transitive, then this relation R in a set A is called a partial order. Let me give you a concrete example of partial order. Let R be the relation in V. V is a set of elements 1, 2, 3, 4, 5, 6, which defines X divides Y. So R to be a partial order, R should satisfy three properties: reflexive, anti-symmetric, and transitive. If we read anti-symmetric part, X divides Y and Y divides X implies X is equal to Y. If we read transitive part, X divides Y, Y divides Z implies X divides Z. Such statement P implies Q, or if P then Q, such statement is called conditional statement. In conditional statement, P implies Q, P is called hypothesis, and Q is called conclusion. The truth table of conditional statement is defined like this. In this conditional statement, if P, the hypothesis, is true and the conclusion is false, then this conditional statement evaluates to false. If hypothesis is false, then the conditional statement always evaluates to true. So if hypothesis is false, we don't need to concern. Now let's compare with this anti-symmetric and transitive. X divides Y and Y divides X implies X is equal to Y. This part is hypothesis denoted by P, and this part is conclusion denoted by Q. In transitive, X divides Y, Y divides Z. This part is hypothesis P, and this part X divides Z is conclusion Q. So if P is false, then we do not need to concern because the conditional always evaluates to true. Okay? Only if hypothesis P is true and the conclusion Q is false, the conditional statement evaluates to false. Please keep this point in mind. Now I will delete these markers. Now let's think about relation R if R satisfies reflexiveness. For every X in V, X divides X. So 1 divides 1, 2 divides 2, 3 divides 3, and 6 divides 6. Every element in V divides itself. So reflexive part is true. Now let's think about antisymmetric. X divides y and y divides x implies x equals to y. 1 divide 2, so 1 divide 2, this part is true. 2 divide 1, this part is false. So this hypothesis is false. So we do not need to concern about the truth table because this conditional statement always evaluates true. So this part is true. 1 divide 3, true. 3 divide 1, false. So this part is false. So it is true. Now let's think about 2, 4. 2 divide 4, true. 4 divide 2, false. So this hypothesis is false. So this antisymmetric part always holds true. For example, 2 divide 2 and 2 divide 2, then 2 is 2. So this antisymmetric part always holds true for all element pairs. Now let's think about transitive part. X divides y, y divides z implies x divides z. In case of 4, 4 is divided by 2 and 2 is divided by 1. So if 1 divides 2, 2 divides 4, then 1 divides 4. Now let's think about 2, 6. 2 divides 6, and let's think about 1 divides 3 and 3 divides 6. So 1 divides 3, x divides y, 3 divides 6, 3 divides 6, so 1 divides 6, x divides z. And let's think about 5, 1 divides 5. This is transitive part of this relation, so it holds. When this part is false, the truth table is always true. When this part is true, when hypothesis part is true and the conclusion is false, then this conditional evaluates to false. Because relation R satisfies reflexive, antisymmetric, transitive in set V, R is called partial order. Please note that partial order allows incomparable elements. What it means is like this. Incomparable elements means something like this. Two elements, A and B, in a partially ordered set are said to be not comparable. If A is not related to B and B is not related to A. In case of 3 and 5, 3 does not divide 5, 5 does not divide 3. So 3 is not related to 5, 5 is not related to 3. Element 3 and 5 are not related, but still exist in the set V. Because partial order allows incomparable elements or unrelated elements, relation R is a partial order in set V. In case of total order does not allow incomparable elements. So this relation R in V is not total order. Because 3 and 5, these are not related to each other. They are incomparable elements in set V. R is partial order but not total order. Understanding the difference between total order and partial order is important. Hi everyone, my name is Thomas Kim. Today is October 15th, 2019. This is my 6th episode about C++ 20 standard core language. In this episode, I will talk about comparison categories and partial order. More specifically, we will learn how to use STD, partial ordering, and STD variant, etc. At the end of this episode, you can double-click this link and download the complete source code. Without further ado, let's get started. Start Visual Studio 2019. Go to File, New, Project. Type in Console App. Select Run Code in a Windows terminal. Print Hello World by default. Select this template. Click Next. Project name will be Comparison Categories. Solution name will be 06 Comparison Categories Solution. Click Create. Right-click the project, Properties. Make sure all configuration, all platforms selected. Click General. Click this button. Click Edit. Click this button. $CPP extension _dir. Hit enter. Then your path should be resolved like this. Click OK. Select language. Select preview feature from the latest C++. Click OK. I will delete this part. Include talk, play, fun, output HPP, include compare using string stream, talk, play, fun, output string stream, talk, play, fun, S stream, stream, auto, and there, talk, play, fun, and there. Void test default categories. int a 4 d 5 double d1 2.0 d2 3.0 auto r1 a b auto r2 d1 d2 stream type of r1 talk, play, fun, get type category r1, and there I will copy this line, semicolon here, type of r2 category r2. Now I copy this function in the function main. Press Ctrl F5. Please understand that when we use three-way comparison operator over type integer, the comparison result is strong ordering. So when we compare integers of type int, C++ compiler returns an instance of strong ordering. When we compare type double using three-way comparison operator, the return type is partial ordering. Please keep this point in mind. Now here, class variant public using value type std variant int std string. We defined a type private value type member variant. We will initialize member to integral type 0. This is default constructor variant int b member b variant std string b member b. We defined three constructors. Now we define an operator like this. Friend string stream. We define the string stream here. Operator string stream os constant variant B OS. B has a member, return OS. Now here we define three-way comparison operator like this. STD, partial ordering operator. This is three-way comparison operator. Constant variant right-hand side. Try auto L this M member. From this member std get int auto R std get int RHS M member. Please don't forget it should be constant. Please note that this member is type variant defined here. If you are not familiar with std variant, please refer to this document. I will copy this link for your reference here. If it fails, catch std bad variant. This type will be thrown. If you are doubt, please refer to this document. For example, std get. If fails, it throws std variant access. This is testing with type int. We can test with type string. std get std string this M member auto R std get std string RHS M member. Now here return. This is integral type defines three-way comparison operator like this. L R. Please note that this comparison operator returns std strong ordering, which is converted to std partial ordering because of this return type specification. Now here, if L is less than R, return std partial ordering less. Else if L is greater than R, return std partial ordering greater. Else L is equal to R, return std partial ordering. It is equivalent. Okay? Now here we will use try catch. Okay? Catch std bad variant access. In this case, we return std partial ordering unordered. If the current type of this M member and the current type of RHS M member are different, that is, we cannot compare int with string, then we return std partial ordering unordered. Now we defined this function void test custom variant. Here I will make assignment operator variant operator int v this M member v return this. I will copy once again, paste std string. Now here variant v1 we will initialize with value 20. v2 we will initialize with value 30. Stream v1 and there v2 y is squiggle. Sorry, it should be public. Now scroll down. Now I copy this function name, copy, paste, and disable this part, Ctrl F5. So far, so good. Now we compare like this. Stream V1 less than V2, V1 less than V2. I copy once again, paste, greater, greater, equal to, equal, equal. Now press Ctrl F5. No binary operator found which take left operand of variant type. I will disable this. Ctrl F5. So far, so good. Now I will define equality operator, bool operator, constant, variant, right hand side, constant, return this three-way operator, right hand side, equal to 0. With this, I will enable this part, press Ctrl F5. Now it works successfully. Now here, V2, I will assign Thomas Kim, and we compare once again, pasted it here, stream, and there. I will also copy this part, copy, pasted it here. Now let's try it, Ctrl F5. So, V1, V2 is integral type. They are compared successfully. When one is integral type, another is of string type, V1 is less than V2 false, V1 is greater than V2 false, V1 is equal to V2, all false, because V1 integral type, V2 of string type are incomparable. So this is the power of partial ordering, unordered. When the current type of this member and the current type of right hand side member are different, that is, we cannot compare int with string, then we return std partial ordering unordered. Also, I will copy this part, paste it here, then we can return like this, for inequality. This is for equality. I hope you understand what is partial ordering. I will upload complete source code to my website. By the time you watch this video, you can double-click this link and download the complete source code. Also note that if you want to download and build my source code on your machine, you have to install my type library. By watching this video, you have to install latest version of Microsoft Visual Studio 2019. Also, you have to download and install C++ library extension. Please subscribe to my YouTube channel. Thank you for watching.